All right, we're going to start today with a quick review of the OLS outputs because there was some confusion, mostly because of me, from Thursday study group. So we're going to go over everything again. This time I have everything written down, also for your reference. These are all very, very commonly asked interview questions as well. So just good to know. So this data set, I'm actually going to use throughout the section 19 labs. They use this miles per gallon data set, and they have some of their transformations done. And we're actually going to talk about transformations as well. So we're just going to run all of this. Did I type in A somewhere? There we go. All right, have this run. OLS model fit. All right, so any questions, please clarify now. Now is the best time to clarify all of this stuff because this is what you'll be doing in your project starting end of this week. So, all right, we fit this model with the dependent variable miles per gallon. And here I'm just using 4 of the variables: acceleration, weight, horsepower, and displacement. These are the unscaled variables. I think that's what we're doing. All right, anyways, scaled or unscaled, let's interpret everything that's in this output that's important to interpret. So first of all, R squared and adjusted R squared are goodness of fit metrics. How well does your model fit the data? And the official definition is that an R squared of 7.707 is saying that our model explains 70.7% of the variance in miles per gallon. So here, I know I ran this with a different random seed, so slightly different. But this model and these independent variables explain 72, or in this case, 70% of the variance in miles per gallon. As I mentioned earlier, adjusted R squared accounts for more independent variables. So as we start building bigger models, you'll see that the tendency is that when you have more independent variables, your R squared usually goes up. So your adjusted R squared just accounts for the extra variables. Cool. Questions on R squared before we move on? All right. Out of this top table, R squared is the main thing that we'll be looking at. Next is this table, and this table has a lot to unpack. First, the coefficients. So coefficients, you have 2 different coefficients. First, you have your intercept, and then you have your independent variables. For the intercept, a 45 for your intercept coefficient is basically saying that when all your independent variables are at 0, miles per gallon is at 45.25 miles per gallon. And whatever the unit is, you have to make sure that you're remembering that. And for each independent variable, for example, a coefficient of negative 0.0231 in acceleration means that a 1 unit increase in acceleration, and actually let's take a look at what acceleration looks like. Data, acceleration. All right, I'm not too sure on like what the unit is for acceleration, miles, meters per second square, whatever it is. A 1 unit increase in acceleration leads to a 0.02 decrease in miles per gallon. And so when you're interpreting these coefficients, sometimes it's important to see, let's say, definitely take into account the scale, but which variables with a unit increase in whatever independent variable, which one can affect your miles per gallon the most. And now, after coefficients, we also got to look at p-values, because one thing that we're really going to look at is actually one of the in the project guidelines, it says that you shouldn't have any independent variables with p-values above 0.05 with your alpha at 0.05 as well. And so for each independent variable, we're actually doing a hypothesis test here. We're actually taking a look to see whether there's a relationship that exists between your independent variable and your dependent variable. So in this case, the hypothesis is testing whether your coefficient is equal to 0 or not. The null hypothesis is that the coefficient is equal to 0. Alternate hypothesis is that it's not equal to 0. So as I mentioned earlier, we're looking to see if there's a relationship between each independent variable and the dependent variable. So if you remember how we set up a t-test, this is literally a t-test. We usually calculate our t-statistic that has an associated p-value. And the t-statistic is calculated using standard error, the coefficient itself, and the mean, and all of that. So anyways, you get to some t-statistic that has an associated p-value. And then this 0.025 and 0.975 values are the 95% confidence interval. So I think I have more definitions down here. T-statistic is the t-stat from this t-test of whether the coefficient is equal to 0. A p-value below 0.05 is evidence to reject the null hypothesis. So saying that there is statistical evidence that there is a relationship between independent and dependent variable. If you have a p-value above 0.05, it is saying that statistically there is no relationship between independent and dependent variables. That is why if you have higher p-values for any of these outputs, you want to take them out. Let's see. And yeah, the p-value is the associated p-value of the t-statistic, and therefore if the t-statistic is outside the confidence interval, the p-value should be below 0.05. Any questions?
Just one quick question. So for the project, are we going to use only the OLS or any other regression model?
For the project, you're actually going to be using a combination of, well, okay, the only model you're going to run is an OLS model. However, there's two different libraries to run OLS models with. And I'm actually going to get into scikit-learn later. But yeah, you're mostly going to be running your models using stats models OLS and also scikit-learn's linear regression model. And I'll explain that later as well. Just because scikit-learn works a little better with like your train test split, which is something that we also have to do. Any other questions?
Now, let's say if this particular thing is also, will you be showing that it will, what are the difference when you run it with scikit?
Yeah, I'll actually be
the
walking through that as well.
Same problem, right?
What was that? What do you mean?
For the same data set, are you going to run the scikit model and then explain how, right, we will be able to understand the difference?
Yeah, for sure. I'll be talking about the both of them.
Okay.
Cool. All right.
Yes, quick question. So just so I can maybe understand this a little bit better. So the so when the intercept, so when all the independent variables are 0, that basically the intercept coefficient, or the intercept is basically saying when all the independent variables are 0, that's the value of miles per gallon, correct?
That's right.
So what is that actually saying about the, how can I say this? All the independent variables, when they're 0, are they still being taken into consideration, and is that showing a relationship with the dependent variable at all?
Yeah, because the intercept actually comes as a result of all of these variables as well. So the intercept is kind of there because we're writing a linear model, and in a linear model, you have to have an intercept. If not, you're kind of forcing when everything is 0 for your miles per gallon to be 0. To sort of maybe illustrate it, if we have, let me see what's a good scatter plot that I can draw on. Let's go with this one. Or no, I actually have a better idea. If we go to here, remember how from your linear regression, you actually come up with this model, you come up with this formula, right? You have to have some sort of intercept term. In real life, it doesn't really mean anything because like it doesn't make sense to have like a net, for example, in this situation, you have a negative weight if you have a height of 0.
Right.
Which I mean, conceptually doesn't make sense in this context, but is to set up the linear relationship between independent variables and the dependent variables.
So basically, it's the intercept. It's not useful for anything outside of just helping us to reference and create a relation and visualize a relationship or understand a relationship between the independent variable and the dependent variable.
Yep, that's a really good way of putting it. Yeah.
Okay, gotcha.
Cool, awesome.
Also, one quick question. Now, currently we are running after we have created those the dummies, and then like we are running all this report.
I'm actually running separate ones. This one I ran actually doesn't have the dummy variables yet. Okay. But yeah, you would be running your model with dummy variables with any like scaling or transformations that you do, yes.
So do we do two different files, or let's say we create two notebooks, one with dummies and one without dummies, something like that?
No, actually what I'm gonna do is on Thursday when I introduce the project, I'm actually gonna like give an outline of the project workflow so that, you know, it'll be a little easier to figure out, okay, when do I do a train test split? When do I run a first model? When do I like, you know, check for all the assumptions, stuff like that. So I'll actually be providing like a notebook that has like a skeleton of your project.
Okay.
And so I think that will make things a lot clearer as to like, you know, what.
Yeah, because I was, before Marvin questioned, I was under the impression that, okay, it's already, the dummy variables have been already run, and then like we are getting all the reports.
Oh, for this, it was just an example that I could use to help interpret the, just to interpret these statistics. But yeah, we're actually going to get to that in a little bit as well.
Yeah, I have a question too. So for those p-values, the only one that's below 0.5 is a horsepower. So when you so that's the only one that you reject the null hypothesis, or you accept the null hypothesis. Wait, how do I say it? That's the only one where you would reject the null hypothesis, and so would you now go forward only using horsepower and forget about the other variables?
Yeah, actually for this model, I would actually first, so because what I would do is actually, because there are only 4 independent variables here, I would actually take out the largest p-value and see how it refits the model to just the other 3 variables. So there's a chance that, you know, in getting rid of this, it fits these other 3 a little bit better. And for example, if this displacement is still too high, then yes, we're only going to use like weight and horsepower to predict intercept.
Weights as well, yeah, that's right. Weights also underneath the
yeah, and if it's the case that even weight, let's say weight is also a p-value above 0.5, it's better to have fewer variables that predict well than having variables that don't actually have a relationship. And that will like have a little bit of an abstract discussion when we talk about the bias variance trade-off in a little bit.
All right, and then Yish, one other question. So about intercept. So all of the other numbers, standard error, t-statistic, p-value for the intercept specifically, that would we ever need to think about those numbers as far as like, for example, like standard error, right? Is that like too high? Is it low? Is it normal? Or are we ever asking those types of questions about those numbers?
To be honest, I have never heard of someone being asked this. And I personally, to be honest, actually I'm not 100% sure of like what exactly the hypothesis is here. I don't remember if it is the hypothesis checking that whether this intercept is equal to or different from the average miles per gallon or 0. So it is also similarly conducting a t-test, but to be honest, I don't remember what the t-test is.
Okay, that's fine.
Yeah, but intercept term is not commonly something that people ask about.
And that's okay. But I mean, just even in terms of understanding the model and understanding the relationships, we wouldn't really need to think about the standard error as it relates to the intercept.
Yeah. Yes. Yeah. You typically don't really have to think about standard error in terms of any of them, because the standard error is actually taken into account when you construct your t-statistic. Yeah.
For sure. Okay.
But I'm loving all these clarifying questions, by the way. All good questions so far today.
Thank you.
All right. We're going to be jumping a little bit back to our past notebook because last Thursday, we didn't talk about transforming features, and we didn't talk about all of train test split and scikit-learn. So I'm going to start back here, talk about transforming features. Transforming features is what you do when you notice that one of your independent variables isn't nicely distributed. Very often you find that variables are actually right skewed. It's a phenomenon that just occurs in data naturally just because of outliers on the high end for a lot of different variables. Very, very generalized here. But for example, something like displacement here, you can see that there's a lot in the low end and it sort of like tapers off. And therefore we have a right skewed histogram. Very similar we have here for weight and horsepower. Why we want to scale is such that there's a stronger linear, not stronger linear relationship, but a more balanced data set. You can see here, because if you have too many values on the low end, you'll have more data points in that region, and you kind of want to balance that out, if that makes sense. It's a very abstract concept, but I will say that log transformation is something that you can maybe test out in your projects. But just to show what a log transform does, and log transform is like one of the more what's the word, impactful transformations, and I'll very briefly describe some of the other transformations that are brought up. But in this case, let's do a log transform on these three features, because these three features look a little bit more skewed, because acceleration looks like it has a normal distribution. And I actually ran it already. You can see here that horsepower, you can see that the mode or the mean is kind of closer to the middle of the histogram, which will make our modeling possibly a little bit better. I say possibly just because you never know about how your other features interact with this. So log transformation is definitely something you can try. Sometimes it makes your model better, sometimes it might not. But transformations is something to just be very aware of. Other kinds of transformations, and so here very quickly you can see that log transformations useful when you don't have a normally distributed feature, reduces skewness, and reduces variability. All of these other scalings, so min-max, standardization, normalization, unit vector transformation, I actually suggest you use if you have variables of very different scales. And what different scales will do is it will make your coefficients sometimes hard to interpret. So for example, if we look over here, we have, let me go to one of our, maybe just go back to this. So here we have, weight, displacement, and weight and displacement are both in like the thousandth in terms of like the scale of their coefficient. And something you can do if you want to make your coefficients a bit more on the same scale, like for example, maybe you want your coefficients to be in like, the ones of digits rather than, 0.006. Something you can do is just rescale your data. A little bit tricky because you would have to unscale it to properly interpret it. But sometimes if you have very, very wide range of data points, if you're predicting housing prices in the millions and you're talking about like, 1 bedroom or 2 bedroom, you might end up with like very large coefficients. You might end up with coefficients like 100,000. So imagine like, increasing 1 bedroom would increase your price of your house by 100,000. And in contrast with other coefficients, it might be very jarring. And that's why we might want to do some of these other scaling. So for example, min-max scaling will bring all your values between 0 and 1. And so all you have to remember is what your minimum and maximum values are, and then you can unscale your data afterwards. One thing to be very careful with min-max scaling, because you're scaling all your values between your minimum and maximum, I highly recommend not using min-max scaling if you have a lot of outliers. If you have a lot of outliers, I wouldn't use min-max scaling. Just because, let's say you have like a couple houses that are like $20 million, and most of your houses are in like the $100,000 to $500,000 range. Your scale or your histogram will have all your points really huddled up in like the 0 to 0.05 range. Does that make sense?
So now, wouldn't it reflect the outliers directly instead of we searching separately?
Can you say that again?
Now, when we, let's say, run the min-max, right? Now, it will also show as a graph, right?
Yeah, it will show as a graph.
Yeah. So when it shows, like in the graph itself, we will be able to identify, right, where exactly the concentration is of,
yeah.
Right.
You would, yeah, you would. But by then, because most of your, because in this min-max scaling, if let's say we have like, you know, your housing prices from like 100,000 to 20 million, 100,000 is going to be close to zero. But 20 million will correlate to 1. And so therefore all your values between 0 and 1 will be very, very highly concentrated between like 0 and 0.1. And that's just, you know, I don't know, it can just really mess with your data and your values and the scale, really.
So now if we run this, right, while we are cleaning or while we are, right, creating the dummy data, right, if we already have run the minimum and maximum value of each, and then, right, only select those columns, right, where we know that, okay, it's not the variance is not very high, and then only for those selected data, if we run this min-max, is it advisable?
Yeah, for sure. I'd say for like when you're doing scaling, I mean, it does differ in like, depending on your data and how well you know it. I actually typically don't scale until after I run my very first model, just to take a look at the coefficients, taking a look at the p-values, especially if it's like a log transform. I'll be actually looking at the output of my very first baseline model before I do any scaling, just so like I wouldn't be scaling if it's not necessary. Yeah.
Because when we run the info itself, like we also get when we run the describe, not the info.
Oh yeah, the pandas, like the pandas functions. Yeah, for sure.
It gives us min-max, right? And within that, if we understand that, like, okay, we only, like, for example, if, right, pricing versus like, if we are not going to, if we run the size of the bedroom, it's easier than running, right, your price with, right, something like a sea facing apartment, you know. It might give a different variance. So if I select only these two, like I want the pricing at that time, I want, apart from pricing, I want have only one independent variable instead of having 2 or 3. And after selecting that, then I run this scaling. It should work better, right?
Yeah. Not confirm that it will work better, but your coefficient will not look as, your coefficient will look more to a scale that might be better, might be more comparable. I will say, like with modeling, there is very rarely like a, this is the right thing to do, which is why it's such an iterative process. It's really like, you can try an infinite number of things, which is why I'm gonna like actually make a list of, you know, possible things to do. And these, everything I'm gonna talk about today are like possible things you can do to your model. And if you feel like your model doesn't need any of these things, don't do it.
Yeah, I mean, because it's like as we get into deeper into it, it's getting more and more into the complicated side of it.
Yeah.
Just,
yeah, for sure. Yeah. But yeah, if there are any like specifics when while you're working on a project, if anything specific comes up, definitely talk about it in office hour or 101.
Okay.
Awesome. Okay, so min-max scaling, you don't want to do it with outliers because it bounds your values between 0 and 1. Very similar to mean normalization and unit vector transformation, because all of these transformations, they have slightly different formulas, but they kind of bound your values between like either 0 and 1 or -1 and 1. And whenever you have bounded values, outliers kind of just like squish all your values together, if that makes sense. The most popular scaling that isn't a log transformation is actually standardization. And what standardization does is actually very similar to finding a z. It actually is the same formula of finding your z-score. It just turns any distribution into a distribution that has a mean of 0 and a standard deviation of 1. Sometimes if you find that your feature set or like all your independent variables have very, very different ranges and scales of values, some people like to use standardization because, you know, it makes all your coefficients on the same scale. And whether that makes sense for your data or not, it really depends on your data set and your context. But this is all the scaling that is available. Cool. Any questions on scaling? There are some pretty good examples in the labs as well.
Just a quick question. If you do a scaling, you should always do it across your entire data set, right? You shouldn't do log transformation for one variable and then standardization for another variable, correct? The same?
No, actually, you can do different scaling on different variables. So every variable can have its own scale, own like scaling. And all you have to do is just keep track of what scalar is used for what variable. What I've seen some people do is, let's say you have like 5 variables with 5 different scaling, you actually like will write a function that will scale and then unscale the values, just so you can keep track. And you can actually use like the columns of your data frame to keep track of that. But yeah, you can do different scaling. And actually in the example right below this, I think, yeah, we'll see that there's different scaling being done on different variables. But yeah, you can definitely do different scaling on different variables. So like in this here, you can see that, let's see, they took the log transform of displacement, horse, and weight. And I guess after that, they rescaled the log transform as well by taking, I think this is min-max scaling for acceleration. Here, it looks like they did standardization. I think this weight is also being standardized. And this is also min-max scaled. So different scaling for different variables, definitely a can-do thing. And actually, let's take a look at what these all look like. I think this is a similar graph, but yeah, you sort of see the effect of the scaling here. The min-max scaling for acceleration and horsepower, so here and here, they are between, let's see. So this one is min-max scaling between 0 and 1. This, I apologize, this is actually mean normalization. They did mean normalization on horsepower, so it's distributed between 0, usually -1 and 1, but I guess none of the values are that far out. And then for displacement and weight, because they did a standardizing, the values are actually unbounded on either side. So you can see it's actually a little bit different.
I'm sorry. So we might do both the log and standardizing?
Yeah, absolutely. You can do both of them, because after you do a log, you might find that the scale of your values are not what you want. Sometimes you just want, you know, all your values to be between like, for like a normal distribution, maybe between like -3 and 3, just so it's more all standard, I guess. But yeah, you can also do other scaling on something that you've already log transformed. All you have to remember how to do after that is be able to reverse transform. So in this case, let's see, for weight, right? For the weight here, they did a standardization. So all you have to do is then multiply it by this variance and then plus the mean value back to get it back to, you know, the unscaled value. And then you have to exponentiate it to undo the log. And you've got to do that to any of your to the coefficient to interpret the coefficient to be more accurate. Sound good?
Are you going to go through an example of like doing it backwards? Like no, I didn't plan to do it, but we can actually take a I'll find an example and I'll do it during either Thursday or during an office hour. But yeah, that's a good point. Okay, cool. Thanks.
Of course. All right, scaling is just one of many things that you can do for the project, not
it's not a mandatory thing to do. So on Thursday, I sort of ended off alluding to train test split and why we need to train test split, basically to validate our model, to make sure that your model can be generalized to outside data, that it's not, you know, overfit on your training data. And that's why we do a train test split. We train our model on usually 80% of the data and test it with 20%. And we didn't really get to this, but I wanted to talk about comparing your doing a train test split with scikit-learn. So scikit-learn is, and I'll get to scikit-learn in a little bit, scikit-learn is another library that does models, has a lot of machine learning models. All of Mod 3, you'll be using scikit-learn's models. So it's a good idea to get used to the syntax of it. For this project, you'll be using a combination of both because scikit-learn does not have this very nice output. So that's one downside. Scikit-learn doesn't have this very nice output, but on the other hand, stats models doesn't have as good outputs for comparing, for validating your model. So it's like kind of pros and cons of both. And so I'm gonna outline on Thursday when to use which. So it's a little bit all over the place here, but I had mentioned why we do train test split, and basically what we're gonna do to check for overfitting or underfitting is compare the metrics between your train test and your test set, between your train set and your test set. So if you remember when we were doing our R-squared, and R-squared is comparing how well the line fits the data points compared to some baseline model. Remember, R-squared is comparing that like best fit line to like that horizontal line. And R-squared is really just like a proportion of how much more variance is explained in a best fit line. In kind of a similar sense, we're using RMSE to check for overfitting or underfitting. So RMSE is very similarly a root mean squared error. So basically a measure of like the average distance away each of these points are from the line. We're gonna compare the RMSE of our training data to the RMSE of our testing data. Now, when something is overfit, you get some RMSE for your training data. So let's say, you know, we're talking about height, and we're doing that like weight and height, and your training data says, okay, on average, our weight is maybe like 5 pounds off, you know, based on like the predictions made, roughly 5 pounds off. If we take our testing data and we get an RMSE of, let's say about 5-6 pounds as well, that's not too bad. But if our testing data gives us an RMSE value of like 10-15 pounds, of course, like the scale of whatever we're doing depends on context, but if we're talking, you know, 5 pounds versus 15 pounds, obviously our model might be overfit to our training data. Does that conceptually make sense? We're gonna go through an example, and hopefully that will make things a little clearer. But any questions about what I just said? All right, we're gonna run this regression again, and we're gonna do a train test split. And so to introduce scikit-learn, scikit-learn works kind of similarly, but in some ways very different from stats models. Stats models, you have that very nice output. In scikit-learn, it's easier to work with train test split. Yeah, so if you remember that at the top, actually, when I was trying to make predictions with stats models, there was no way to make a prediction without first writing this function of like predicting weight. The plus side of scikit-learn is you can just feed it in any numbers and it'll give you a prediction. Whereas in stats models, it wasn't able to make a prediction on an out of sample data point. Cool, all right. So back to scikit-learn. So the way you set up scikit-learn is you actually have to separate your independent and dependent variables. And typically your dependent variable is y, and your independent variables are x. Small letter y because it's one column, big letter x because it's multiple columns. That's just the syntax that is typically used. So we have our y and our x's, and then you do train test split. And scikit-learn also has train test split built in. So here you can see I am importing from scikit-learn, and scikit-learn has a lot of sub libraries as well. And we're going to see actually quite a few of them in these next few cells. But here we can import train test split. And train test split works very interestingly because you are assigning 4 variables at once. You're assigning the x train, x test, y train, and y test all at once to this output of train test split. So actually, let's take a look. Random state is sort of like random seed, it is the same thing as random seed. And test size basically will tell you what proportion of your data set you're going to use as testing. And in this case, we're going to use 20% as testing because 80% is training. So let's run this and take a look.
One quick question. Now, the X train, the alphabet is right, the capitalized.
Yeah.
But like for Y train, the alphabet is not. So
Yep.
Why that difference?
Yep. Just because Y is just one column of data, right? Your dependent is just one column, and X is big because you have multiple columns in X. X is all of your independent variables. We can actually take a look right now. Let's take a look at X train. X train are, in this example, I guess, it's acceleration, weight, origin 2, and origin 3. And you can see that it shuffled it to randomly select 80% of the data. And this is X train. As an example, let's take a look at Y train. So Y train is just the miles per gallon that are associated with these. So you can see it's 262.113, 262.113. Scikit-learn just needs us to separate these. And just really quick.
In our data, it will be like the Y train if you're going to do, let's say, pricing. So the Y train will be only pricing and everything else will be X train.
Yep, that's right. That's right. And just to quickly look at X test, this is just 80 rows. And actually, like, let's go back and look at X train. X train was 317 rows. X test, 80 rows. So roughly a 80-20 split. And X test looks like this, and Y test looks like this. So again, they're associated with each other because it keeps the index there. All right, so that is the line for doing a train test split. So once you do your train test split, we're going to fit our model. Kind of in a similar way, you have to first instantiate a linear regression model. So here, what we're doing is we're saying, all right, to linreg, the variable linreg, we're going to give it an empty linear regression model first. And so that's what this first line is doing. We're instantiating an empty linear regression model. What this second line does is it takes this empty linear regression model, linreg, and it fits the model to the training data. So we're fitting it to X train and Y train. So this line is doing all that calculation of what the best fit line is, of what the model is. And then, who remembers what Y hat refers to? I know we've seen a lot of Ys. We've seen Y hat, Y bar, regular Y. Anyone have any memory of what Y hat is?
Is the mean?
Y hat is not the mean. The mean is Y bar.
Y
It's the
bar.
estimate. It's
Yes,
the estimate.
Y hat is the estimate. So Y hat is basically the value at whatever X that lies on the line. So if we just take a look at, let's see, where is there a scatter plot that I can use? So yeah, let's take this one, for example. Where's my annotate? So just for a quick refresh, if this is our model, Y bar is whatever the average is. So this is Y bar. Y bar is just one value for all X's. Y bar is the average. And let me just write that down. This is Y bar. Y by itself, if it's just Y, or sometimes you'll see YI. YI, and let's do it per point. So let's just take this point. For this point over here, YI is its actual value, either Y by itself, or sometimes you'll see Y with a small I. That's yi. Y hat is the predicted value. So even though this point is here, if we were to run, you know, height equals to 71 into our model, y hat, which is the predicted value, is, let me take this here, is actually, you draw it down to the line and then see where it is here. So this red value here, that is y hat. Does that clarify things? So y hat, and usually anything with a hat value is a value that you get from your model.
So now it will be like, okay, more all the time the the data point will be on the line when you have to figure out the y.
Y hat is always on the line, yes.
Okay.
Yeah. All right, so y hat is always on the line. So what we're doing now is we're finding for each of the data points, what are the values that lie on the line. So let's clear this and let's go back down to what we were doing. And basically comparing the y hat to the original y is how we get our root mean squared error. Because, and I'll actually go back and talk about that, I should have mentioned that earlier. Our root mean squared error is done by, let me just quickly draw all these lines back. Root mean squared error is comparing, and then let's do this for a couple lines, is comparing for this point, let's start with this point. Root mean squared error is comparing this y value to this y value. Because this bottom value, this is the prediction, but this is the actual. And we actually, for every data point, want to see what this difference is. Sound good? All right. So,
Yeah.
Oh, sorry, I think you're muted.
Yeah. So the better model will be the, when the difference is very low.
Yep, that's right.
Yep. Oh, yeah.
All right, so back down here. Okay. Here what we did is we're finding the predictions for all of the x's. So for all the x trains, there's an associated y hat, and for all the x tests, there's an associated y hat. So actually, let's take a look at what these look like. Y hat train is just an array of values as well, and y hat test is an array of values as well. And what we're going to do is we're going to compare y hat train to y train and compare y hat test to y test. Because y train and y test are the actual values of the data points, where y hat train and y hat test are the predictive values. And we want to compare those to get our root mean squared error. So to do this, you can see that sklearn also has, it actually has mean square error, but not root mean squared error. So I'm actually going to do I'm going to do the square root down here. As you can see, I take to the power of 0.5. But mean squared error, you can just feed it in y train and y hat train, it'll compute that error. And there we go. You can see that the train error is 15, the test error is 21. Because this is squared, we're actually gonna take the square root. The train root mean square error is 3.97, test root mean square error is 4.59. So how we evaluate this and what this means is that in our testing data, on average, our model predicts 4 miles per gallon off. Roughly 4, or 3.97 gallons off. And in our testing, it actually predicts 4.6 miles per gallon off. And so whether that's overfit or not, because our testing data usually typically should have an error value slightly higher, whether this is considered overfit or not, you have to take a look at context. Like if, predict them by like 0.6 miles per gallon off, is that a big difference? I don't know cars too much, but yeah, I would say this is a pretty okay model. Questions on that?
And just to review the test data, that's stuff that was randomly generated from the model.
The test data is not randomly generated. The test data is we had split all of our data points into 80% for training, 20% for testing. So we actually had 20% of our data points just left aside that we only use for testing.
I see. So you're taking that test data and you're applying it to the model that you made with the training data.
Yeah, it's really just to simulate if your model can work on unseen data.
Okay.
Yeah. I mean, ideally we want to have more training data, but if we use all our data for training, if we use that to test as well, it kind of doesn't make sense, because why would you test something that it was trained on? It'll take a little while to like get used to this. Let me see. I actually installed a light here. Okay, there we go.
Okay, can you just try and increase it to 30 instead of 20%? So
Oh, yeah.
30.
For
So,
sure.
yeah, when we do 30,
Mhm.
what is the difference that comes in?
So let's see. Actually, it looks kind of very similar. I mean, I'm not too sure in the context of cars what that means, but earlier was 3.9, now it's 3.8, and earlier was 4.5, now it's 4.6. So you can see that the spread kind of widens because you're actually training on less data, so it has less representation, and then because of that, it leads to a bigger spread in the errors. Cool. All right, that took a lot longer than I expected, so let's try and get through as much else as we can. So we just talked about doing train test split, but train test split can sometimes be biased by how it splits. What if by some like randomness, you happen to split where like 80% of your points just happen to be newer cars and 20% of your points happen to be older cars? And so what your split is can sometimes lead to biases in your model. And so there is this further validation step called cross-validation. And the idea of cross-validation is also called k-fold cross-validation. Is what you're going to do in k-fold cross-validation is actually divide your entire data set into k parts. So for example, 5 parts, you're going to divide your data into 5 parts, so 20% each. And for 5 times, you're going to take turns holding out 20% and then training your data on the other 80%. Do that for the rest of them, taking turns, which is the 20% that you hold out, and then average your root mean squared error. Just quickly to illustrate why we need to do that. This is just taking random train test splits, and this is a test set of 0.33. So this is the same data, same regression. And what we're doing here is we're running it 20 times to see how our train and test error will vary depending on train test split. So you can sort of see here, our training error varies. It varies not as much, but still a good amount. Like you can see that it varies from about 8 to maybe close to 11, a whole 3 miles per gallon up and down. And our testing error goes up and down between like 7 and 12. And so these are all doing single train test splits just 20 times. And you can see that it varies a lot. And so because of that, we want to do multiple train test splits per model. And so what we can do here, just to quickly talk about it, we can do cross-validation. And what you do here, you can find a cross-validation score. So what will happen here is we're running our linear regression model, and because cross-validation is 10, it's going to do 10 times, train on 90%, test on 10%. It's going to do that 10 times. The scoring for some reason is negative mean squared error. It literally just negatives your mean squared error. We'll take a look at the results, and you're going to take the mean. This shouldn't be 5. This should be 10 because I was doing different ones. But what we'll do here, all right, so we run this. They're doing train test split 10 times, and these are the different errors. These are all the different errors, and then you're just looking at an average error. And you can see by doing it 10 different times, each train test split has like, it can vary from 28 all the way down to 4. And so this is squared, just remember this is squared, so it's actually more like around 5 and 2. But we want to do cross-validation just to make sure. And similarly, you can do this with 5 as well. You can really do any number you want. But cross-validation is basically an extra step that you do to make sure that your model isn't overfitting to any subset of your data. Sound good? Where this fits into the project, I will put it in an outline when I introduce the project on Thursday. All right, let's see how much we can get to. All right, let's talk about the bias variance trade-off now. So this kind of comes hand in hand with what we were talking about with cross-validation and train test split. The ideas of underfitting and overfitting, which we saw this diagram earlier as well. Some other terms for overfitting and underfitting are bias and variance. This is another very, very common interview question. Sometimes it's like, what is the bias variance trade-off? And also, what to do if you have bias or what to do if you have variance. And so bias variance trade-off is basically finding a sweet spot between overfitting and underfitting. You basically don't want to overfit your data because then your model won't be good at generalizing. It won't be good at predicting outside data. But you also don't want to underfit because that means your model won't even do anything. Your model won't even be able to predict. So bias happens when a model cannot learn the training data and also cannot generalize to new data. And then overfitting happens when it learns training data too well, and so it's not generalizable. As we go through the course, a lot of it will come in mod 3. We'll talk about ways to make either of these better. But just to be aware that there's always a trade-off between overfitting and underfitting, and that's actually something that a lot of data scientists deal with. This is more of a conceptual section. Questions? All right, let's try and talk about, in these last 7 minutes, let's try and talk about interactions. All right, so interactions, when would you think about using interactions? You might think about using interactions if, let's say, some variables by themselves are not very predictive, but perhaps the combination of variables could be predictive. Sometimes it's not very clear, but sometimes it is. Like, for example, again, with the example of like, will it rain or not? Sometimes you want to look at cloud cover and temperature. So maybe cloud cover by itself doesn't have like a good linear relationship. Sometimes temperature by itself, not a great linear relationship. There's a chance that if you multiply them together and interact the two terms, you might get a linear relationship, and therefore it might be a good predictor to use. So in this example I pulled from the labs is we're looking at the interaction between the age of a car, like how old the car is when the model year was, and also the car's horsepower at predicting miles per gallon. And so there's a hypothesis that maybe if we interact the year term and the horsepower term might be a good feature. So one way to look out for interactions, there are a bunch of graphs that you can actually plot to see whether interactions are something that you might want to do. In the labs, it actually walks through a process of interacting all your variables together and then whittling it down to the ones that make sense. But if you already have like a hunch on what you want to interact, this would be a way to do it. So in this case, what you want to do is, especially if your data is continuous, is to actually split them into groups. And based on your hunch, maybe there's a different relationship between miles per gallon when you have older cars and younger cars. So in this case, what I'm going to do, I'm going to split my data into older and younger cars. And this is just finding out that the older cars are the ones with dummy variables up to 75. Oh, actually, like this. All right. And let me actually make sure that I'm running the correct version. Yeah, this should be fine. If I run into an error, we'll find out. All right, so what we'll do here, how you figure out whether a variable can interact or not is actually to do single regressions between different parts of the data. Let me actually run this to see what it means. Okay, a lot to unpack here. First of all, what we're doing here is we're running two separate regressions. One with this red line is younger cars, this blue line is older cars. And what it's showing is there could be a different relationship between horsepower in older cars and horsepower in younger cars. So basically what we're saying here is that if we were to interact these terms together with horsepower, there could be a linear relationship with miles per gallon. I feel like the sentence didn't super make sense. But does anyone want to clarify anything?
So you're saying that the younger cars and the older cars, that there may be a linear relationship if you separate them.
Yes, they might have different linear relationships if you separate them.
Different linear relationships, right? Okay.
So actually, let me scroll up one up. If we were to do separate linear regressions for horsepower and the older cars and horsepower and the younger cars, you can sort of see here, and this is actually pulling out the coefficients. The coefficients are quite different based on scale. You have to know about scale, but you can sort of like confirm that, all right, it seems to be a different gradient or a different relationship when you're looking at older and younger cars.
So then sometimes would you say that if you were to do this, like do the interaction test, that sometimes you could find that a segment of the data has a relationship or more linear, or maybe a linear relationship with the dependent variable, when maybe when it was all together, it didn't really show much of a linear relationship?
Let's see. Where a segment of the data could have a linear relationship, but not all of it.
Yeah, so let's say all the cars, like all the horsepower, if you look at it, maybe it didn't really have a linear relationship with miles per gallon. But then if you separated and looked at older cars and younger cars, maybe if you took out the older cars, for example, then all the younger cars say, oh, there actually is a linear relation, a better or more significant linear relationship.
Kind of, yeah, kind of, but you're also to keep in mind that you are still using all of the cars to make your prediction. You're just trying to discern whether there are patterns within segments of your data. But yeah, you can sort of garner that information, but because you still have to, use all your data points to train your model, the interactions actually, we'll see how the interactions actually come into play and make the model better.
Yeah, that's what I was going to ask is, well, in that case, how do you use that?
Yeah, it's actually pretty cool. So here you can see that if basically when you plot this graph and if the lines intersect, is basically saying that there's a different relationship between older cars and younger cars. Like older cars have one kind of relationship, younger cars might have a different kind of relationship. And that is a sign of possibly an interaction. So if you were to do this, but maybe not with horsepower, but with like acceleration, with, I don't know, what were the other one? Maybe like origin or something, you might discern that there are different relationships. And if you're doing like older and younger cars with another variable that maybe results in more parallel lines, then there isn't as much of an interactive relationship. A little bit hard to interpret, but usually what I remember is if the lines intersect, interaction, try an interaction. So what we'll do here first is to try out one model without the interaction to see how it works. So what we're doing here is we're doing a new linear regression. We're doing our k-fold cross-validation. For efficiency's sake, we're just going to do 3 splits for now. And with the cross-validation, what you can do is actually tell it which score to give you. So earlier, remember, we were looking at the negative mean squared error score. You can actually check out the R squared when you're doing cross-validation. Let's take a look at what this baseline model gives us. This baseline model gives us an R squared of 0.832. Not too bad. What we're going to do here now is we're going to add a new variable. So what I did here, make a copy of X and call it the interact one. And then we're going to make a new variable that is literally horsepower multiplied by model year. And we're going to run that regression again, same cross-validation score. You can see that the R squared actually goes up by almost 3%. So this interaction variable actually helped. now to just show this in that OLS output to see if it's a significant variable. And it's not always the case. It's not always going to be the case that it's significant. But in this case, let's see. R squared, actually now it shows us a better R squared because it's a different split. But here we have horse here. Our horse here, this is the coefficient, and our p-value is 0. So there's actually a very strong relationship between the interaction of horsepower and model year with miles per gallon. When it comes to interactions, there's many, many different ways to go about it. As I mentioned, if you don't know too much about your data set, you might want to take the route that the labs go through with like, interacting every single variable together and then looking based on like p-values, which interactions are useful. I will say interactions are also not a must in this project, but if you want to try them out, please do. So interactions, just to like summarize this section before we end off, interactions is when you have a hypothesis that there might be a linear relationship with a combination of variables, then you might want to try an interaction with that in your model. Sound good?
Yeah, just one quick question. So now in the data set that we have in the project, there is one which is like, okay, the year when the property was built, and the data actually is only for 1 year. I mean, all the pricing is given only for 1 year when I saw it. So if we are to find a linear relationship, like where we say that, okay, for year build, which was before, I mean, it's almost 100 years, I think, where when it was built, the property. So if we are going to split it in this similar fashion where we say that, okay, any property which is below, or maybe like we split it into 5 different parts, like how the pricing changed, which are the properties which properties were actually bought during this particular year, only a single year. So where the property, the older ones or the newer ones which were being bought again.
Yeah. And you would basically like plot a graph like this. And let's say, even if you split it into 5, you'll just have 5 separate lines. And if they intersect, also depending what other variable you are hypothesizing to interact it with. So let's say maybe you think like, age of the house, age of the property has an interactive relationship with, I don't know if there's like, if there's a variable in like style of architecture perhaps, or I don't know, something more common like square footage maybe, like maybe now they're just building smaller houses, I don't know. You could definitely like plot a graph like this and see if there might be an interactive relationship.
Okay.
Cool. All right, before I end off, the very last section here is polynomial regression. Just like a precursor to what it is, imagine interaction variables, how we're multiplying variables together and we're saying that, there might be a linear relationship between dependent variable and a combination of variables. Polynomial regression is basically saying that there might be a relationship between the dependent variable and also maybe the square of one of the independent variables, or even the cube of the independent variable. And we will look at some examples, I guess, on Thursday. But I know we're a little bit over time. Does anyone have any questions right now? All right. On Thursday, what I'll be doing is finishing up this. I will also be going through what was expected for the Mod 2 project. I will also be giving y'all an outline, a suggested outline of like how the project process should be. And hopefully that'll be helpful in like organizing all these things we talked about in these past few sections. But all right, have a good night, everybody. Hope you had a good Monday, and I will see you all at your one-on-ones or at the next study group. All right. Good night, everybody.